So today we'll be studying about equations of lines and planes. Lines and planes in three dimension. So why we are doing the equations of lines and planes in three dimension and not two dimension? First of all, for planes, in two dimension we only have one plane, that's the xy plane, so we really cannot explore them further. Equations of lines in real life scenarios, whenever we are studying any object, any line, any curve, it's all in three dimensions. So it is useful to have some background knowledge on how to get some equations, how to analyze equations of lines and planes in three dimensions. Just to refresh our memory, let's take a line in two dimension in the xy plane. This is the y-axis, this is the x-axis, and we have a line here, a random line, okay, a simple random line L. To talk about this line, to represent this line, we need two things. The first thing we need is a point on the line. Okay, the point on the line, we can take any point right here, P. That's over. The second thing is we need the direction of the line. Direction of the line. The direction of the line can be achieved by two different methods. The first method is the gradient, which is the rise over the run. So rise over run, this is the rise, this is the run. So we have the gradient. In some books, you will see there it's mentioned as slopes. Slope. And then there's another method through which we can identify the direction of the line, which is the angle to the horizontal or the angle to the vertical. Most commonly, the angle to the horizontal is used. So the angle. Okay. Now, to summarize, to know about a line, to represent a line in any dimension, not only in two dimension, like in two dimension or three dimension, we would need a point on the line and a direction of the line. In two dimensions specifically, we would need the direction of the line can be given by the gradient and the angle. Now let's consider the same line in three-dimensional axes. Okay, so let's draw the three dimension, which is the x, y, and z plane. So we have the z-axis here, we have the y-axis here, and we have the x-axis right here. This is the origin, and let's draw this line L again. Okay, our random line L. The point on the line, we can have this point right here, which is P naught. Let's tell them this is P naught, and P naught is given by the coordinates of x naught, y naught, z naught. Okay, but now there's a problem. The direction of the line, the gradient of the line is not possible because we cannot measure the gradient of the line in three dimension. In which direction shall the gradient be? If you tell the gradient the slope is 3 upon 4, is it 3 on the z-axis, 4 on the y-axis, or 3 on the y-axis, 4 on the x-axis? We really do not know. So the gradient of the line is not applicable at all for three-dimensional lines. Now the angle is also not possible because angle on through which axis, sometimes the line is passing through all the three planes, the zy plane, the zx plane, and the xy plane. So the angle on which axis, it's making several angles. So we really cannot even play with the angle of lines in three dimensions. So what we have to come up with a direction is given by a vector parallel to the line, a vector parallel to the line. This vector is given by, let's say, v. Okay, and v, we can write v as, vectors can be represented by this kind of bracket, so we can write v as a, b, c. Okay, this is v. Now let's consider another arbitrary point in this line. I'll remove this. Let's consider another point on the line, which is an arbitrary point, P naught. P naught is already, we have P naught. Let's consider P. This is an arbitrary point. So the P can be given by the coordinates of P are X, Y, and Z. Okay, this is the arbitrary point. Now let's draw some vectors. We have a vector here, and then we have a vector here. Let's give them direction. So this is the directions, because without directions, vectors are meaningless. So we have these vectors here. Now let's write down the vectors. Let's give some names to the vectors. So we have vector OP naught. We can write this vector as R naught. So for the simplicity, vector OP, we can write this vector as R, and vector P naught P, we can write this vector as A. So let's name the vectors here. R, this is R naught, and this is vector A. Now I'll just remove this part since we have already written down this part. So I'll write the vector P here again somewhere. P is given by X, Y, and Z. Okay, so now let's draw this triangle separately. This triangle, like this OP naught P triangle, this triangle, we can draw this separately. Okay, so we have here, this is the vector R naught, this is the vector A, and this is the vector R. Okay, now to find the vector R using law of addition of vectors, law of triangle in vectors, we can say that R is equal to R naught, we start from the tail, we end up in the head, plus A. Now we know a very interesting factor about A is that A is parallel to V, as mentioned before. So A can be replaced by T into V, where T is a scalar parameter. A scalar parameter. So T is a scalar parameter. What does a scalar parameter means? Means that as you change this parameter, the position vector R will change. So let's consider my hand. As you change my hand, as you change the parameter T, as you change the parameter T, my hand will move along this line. My hand is the position vector. So R is a position vector. So as you change this parameter T, the tip of the R will change along this line, and you can just join all the dots and then make this line L. This is how it is being described. In other words, R is a position vector of all the points along the line T, given that you change the parameter T. R is a position vector of all the points along the line L when you change the parameter T, the scalar parameter T. Yeah, I'll remove this. I'll remove this part. Now we know that we have given R, the vector R, we have given this. We can write the vector R as X, Y, and Z. Okay, let me just write down a little bit smaller so that I can accommodate the equation in one line. X, Y, Z is equal to, and then I have written R naught plus TV. I have written that vector V, if you remember, I have written vector V as ABC, vector R, I'll just write them down again here so that it's not confusing. Vector R as, I have written vector R as X, Y, Z. Okay, and I have written vector R naught as X naught, Y naught, Z naught. So if you plug all these information into this equation, you will see that you'll have X naught plus TA, then you'll have Y naught plus TB, and then let me just remove this part, and then you'll have Z naught plus TC. This will be the vector equation of the line L. But now, if you want to write a scalar equation, the scalar equations are given by x is equal to x naught plus ta, y is equal to y naught plus t b, and z is equal to z naught plus t c. These are the scalar equations. So these are known as scalar equations of the line L. Okay, now we can find another set of equation which is called the parametric equation. The parametric equation is found by making t the subject of the formula. So it will be x minus x naught over a is equal to y minus y naught over b is equal to z minus z naught over c. This is a parametric, this is the parametric, or sorry, this is the symmetric equation. This is the symmetric equation. And this is the scalar or the parametric equation. This is the symmetric equation. So we have three ways of representing a line in 3 dimensions. We have the vector equation, we have the scalar or the parametric equation, and we have the symmetric equation through which we can represent a line in 3 dimensions. So we have learned how we can do the equations of a line in a 3 dimension. Now let's move on to the next part, which is the equations of planes in 3 dimensions. So I will just remove this all. Okay. So let's draw a plane first in 3 dimension in the XYZ plane. A random plane. I actually do not know the equation of this plane. We will derive it. So this will be Z, the y-axis. I may have mentioned this before. The axes can be anywhere around. It does not matter as long as they are 90 degrees from one another. Yeah. So let's have this plane. This is a plane in the XYZ plane. Okay, we have to find its equation. As usual, we need a point on the plane. Okay, P naught. This point will be P naught, and I'll give the coordinates of P naught here. X naught, Y naught, and then Z naught. Okay. Now we need another point, an arbitrary point on the plane, as usual, as we did with the line. So we'll take an arbitrary point, P. Yeah. This P will be, it's an arbitrary point, X, Y, and Z. Okay. Now here comes the dilemma. The dilemma is we need a vector which is showing the direction of the plane. So can we have the vector which is parallel to the plane? I mean, is it any use to us? It's not, because that vector can be in this direction, in this direction, in this direction. It can be, the vector which is parallel to this plane can be in any direction for we know. So what we will do in this case is we will take a vector which is perpendicular, to the vector P naught P. So this vector, and we will call it N, vector N. So we have taken a vector, okay, N, which is perpendicular to the vector P naught P. Let's do the vector P naught P. To find out the vector P naught P, we'll first draw from the origin OP naught and OP. So these are the directions. Okay. So to find P naught P, let's separate this triangle out so that we can use the vector law of addition in triangles. Let's separate the triangle out. Okay, this is a triangle, and let's give directions. Okay, so now let's name them. Let's name the vectors. We'll name them OP naught is equal to R naught, OP is equal to R, and P naught P is equal to negative R naught plus R. You see this? We start from the tail and we end up in the head. So negative R naught, because we're going in the other direction, plus R. So we can write it as R minus R naught. Okay. I'll just put the names here also. So negative R naught. This is R naught, R, and this is R minus R naught. So now let's move on to the next part. We said that the vector n is perpendicular to the vector P naught P. That means perpendicular to this vector. When any vectors, they are perpendicular to each other, their dot product is 0. Why is their dot product 0? Let's find out why. So for example, we have the vector n, the dot product with the vector R minus R naught. Why is it 0? Okay, let's find out. We know that we'll take the magnitude of the vector n into the magnitude of the vector R minus R naught into cos of the angle between them. So what is the angle between these two vectors? I said they're perpendicular, so the angle is 90 degrees. So when the angle is 90 degrees, it shows that the dot product cos of 90 is 0. So the dot product between the two vectors is 0. If you expand the bracket, we'll have this function right here. Okay. This is the vector equation for the plane. This is the vector equation for the plane. So now we have found out, what we have found out is the vector equation of a plane. But now let's say something. Let's say we got a question. In a question, usually what we'll have a point in the plane, and then we'll have a vector which is perpendicular to the plane, and we can find out the vector equation of the plane. So now let's say that n was given to us as the vector a comma b comma c. So n is given to us. So now we can go ahead and find out the scalar equation of the plane. So for that, I will remove this part. So now let's find out the scalar equation of the plane using this formula. And we have the values of R naught. We don't have the values of R minus R naught, but we do have these values right here. What is R and what is R naught? So let's just find out. So OP naught is R naught and OP is R. So n dot into R minus R naught. So let's find out that in terms of, so we can substitute these into this equation and we will have the scalar equation for this plane. So let's do that. So n is the vector a comma b comma c into R minus R naught. We can write it as x minus x naught, comma y minus y naught, comma z minus z naught, right there. This equation, I'll just remove it from here and I'll write it somewhere else, is equal to 0. I'll write the general equation here. Okay, this is a general equation. Now let's actually do the cross product, dot product, sorry. In dot product, we multiply the first term of each vectors with one another, and then add it with the multiplication of the second product of them, and then add it with the multiplication of the third product. So let's see how it goes. It will be a into x minus x naught plus b into y minus y naught plus c into z minus z naught is equal to 0. So this thing here, we call it the scalar equation of the plane. So now it depends on the question, whatever you're going to be asked. If you're asked to do the vector equation, you go for this. So this is the vector equation, or you can expand the bracket and write it the other way around. It's fine. You can expand the bracket and write it as this thing. You can write it as, it's completely fine if you do that. Okay, it's completely fine if you do that, and or you can write it in the scalar form if the question asks you to do that. Now there is one more thing I need to mention. So if that thing is, if you're given a point and you have to find the distance of that point from a particular plane. So let's say we have a plane. Or random plane, it can be any plane, we don't care. But we know what's the general equation of the plane. We have derived few minutes before. Is equal to 0. We have derived this equation as the scalar equation of a particular plane. We don't know what that plane is few minutes before. And so let's expand the bracket. Okay. After expanding the bracket, we can write it in this form. See that, minus ax naught minus by naught minus cz naught is equal to 0. So now we can see that from this part onwards, this is a constant. Okay, this is x naught minus ax naught. So this is a constant. So this part, so minus ax naught minus by naught minus cz naught can be written as d. Hence the equation of the plane becomes ax plus by plus cz plus d is equal to 0. So let's say that the equation of this plane, we don't know, but in general terms will be this thing. Okay, in general terms. So I'll just remove this. We'll keep this in mind. I'll also write down here what d is so that we don't forget. I'll write down here what d is. D is minus ax naught minus by naught minus cz naught. Okay, let's take a point here, P, which is not in the plane, and we'll call it P1. Yeah. The point P1 can be given by P1 is equal to x1, y1, z1. Okay, there is a point P1. We need to find this distance. We need to find the distance of the point P from the plane. So we are concerned with this distance right here. Okay, the perpendicular distance from of the point P from the plane. Okay, so now to do this, we'll have to consider certain things. Let's take another point. Let's say this point is here, P naught, on the plane. So P naught is equal to x naught, y naught, and then z naught. Remember, the point P naught is on the plane. Let's draw the triangle. Okay. When we draw this triangle, we can give the vectors. Let's name this vector P naught P1 is B. B is equal to, the vector B is very easy to write since it is starting from P naught and ending at P1. We can easily write the vector V as x1 minus x naught, comma y1 minus y naught, comma z1 minus z naught. Okay, now this is the angle theta. This is the distance we are concerned. Okay, now we need to find the distance here. So usually in vector terms, what we say is we need to find the projection of the vector B onto this line, onto this vector. Yeah, we need to find the projection. So let's say, we have to derive the formula for the projection. Give the vector D a name, a value. The vector D can be written as, okay, now we have to find the magnitude of vector D, which is a distance from the point P1 to the plane. Okay, now here is an issue. We do not have, it's a vector, we don't have values, we have to derive the formula. So what we can do is, using the laws of triangle, what we can do is we can write this formula: the magnitude of the vector B cos theta. Theta is this angle right there. Yeah, we can write this formula. Now the next step, the next step will be, so that it does not make sense because we will not have the value of theta, obviously, so we cannot use this formula. Okay, let's do something else. Why not multiply and divide by the magnitude of vector D? And then we'll also divide so that the original equation remains the same. Okay, we did this. This is a good part. So you know why we did this? So that the original equation remains the same. We multiplied by the magnitude of vector D and we divided by the magnitude of vector D. Yeah. Now the numerator is very familiar to all of us. We all know, in this video I have mentioned, or from your previous knowledge, that the numerator can be written as the dot product of vector B and vector D over the magnitude of vector D. Okay, so why I did this, because I didn't want the cos theta here. Okay, why I didn't want the cos theta here? Because we don't have the value of theta. Maybe in the question you will not be given the value of theta. You will only know the normal vector D to the plane. You will know the point, okay, and you will know any point on the plane, and you will know a point will be given to you, and you'll be asked to find the distance from that particular point to the plane. So now let's go ahead and expand this so that we can get a formula we can use. I will rub this previous part. Before rubbing the above parts, I will write down certain things here. Maybe I'll write down vector B here. So when we input that, we don't have an issue. The vector B is x1 minus x0, y1 minus y0, and z1 minus z0. And the vector D is, okay, so this is the vector D, okay, and let's mention the points P1, P0. I don't think we need to mention those points. Yeah, we don't need to mention those points. Okay, so let's do this right here. We know the formula is the distance D is equal to okay, so if you put in the terms, so the dot product of the vector D and B, so this is the vector D, the dot product will be A into x1 minus x0 plus B. Let me just write this down neatly so that it's noticeable to everyone. I'll use this space here so that we get more horizontal space. So it will be, the dot product will be A into x1 minus x0 plus B into y1 minus y0 plus Z into we will have Z into plus C into, sorry, plus C into Z minus Z0, and then divided by the magnitude, we will divide it by the magnitude of D, which is square root of A square plus B square plus C square. Yeah. Now let's expand the numerator. When we expand the numerator, we come up with AX1 plus BY1 plus CZ1, here this is Z1, okay, minus all the negative terms, AX0 minus BY0 minus CZ0 over the denominator, which we already have. So now we remember that this part, we know this part. Sorry, this is not positive, this is negative. This part, we know this is D. We have written it right here. So from there, we can write down that as, this part is D. From here, we already derived it before. We can write down this as AX1 plus BY1 plus CZ1 plus D over square root of A square plus B square plus C square. So guys, we have derived the formula of the distance of the point P1 from the plane. Okay, P1, these are the coordinates of the point P1 from the plane ax plus by plus cz plus d. Given the normal vector of the plane is d, which is a comma b comma c. So this is the end of the video for the equation of the lines and the planes. To summarize what we have learned today, where we have learned how to find the symmetric equation of a line, the parametric or the scalar equation of the line, and the vector equation of the line. Then we have went on and learned how to find the equation of plane in the vector form and in the parametric or the scalar form. And then we have derived the distance of a particular point from a particular plane, the formula. The next video, we will look at some of the exercises or some of the examples which will actually make all these derivations more clear. So if you have any questions, please put them down in the comment and please subscribe to my channel.